Okay, today's lesson is solving systems of equations by graphing, and I'm hoping that you'll be able to determine by the end of the lesson if a system is consistent or if it's inconsistent, and if it is consistent, whether it's dependent or independent. This is standard A.REI.6, which is solve systems of linear equations exactly and approximately, focusing on pairs of linear equations in two variables. Okay, so first, I've kind of got an overview here. I hope you can read my chicken scratch. What I always tell my students to do is first put the equation in slope-intercept format. Y equals mx plus b. That way it's easier to graph. And of course we know from there to always graph the y-intercept. Then we use the slope, that's the m, the change in y over change in x, to find our next points. And we do that for both equations, and then we look for the point of intersection. So once again, I like to always plug in all the information that I know. So I've got y equals 2x, so I know that's plus 0 if there's nothing there. And then for the bottom one, y equals negative, there's an understood 1 over 1x plus 3. So let's start by graphing the red one, since I've got the red marker up. We graph the y-intercept first, so I'm going to go up here to 1, 2, 3 and put my point. And then my slope is negative, so I know my line is going to be moving down as I read left to right. So I go down 1 over 1, down 1 over 1, down 1 over 1, and I keep on going. And I'm going to go the opposite direction as well, and then I can draw in my line. Okay, let's go ahead and plot our green one. The top equation, y equals 2 over 1x plus 0. So I want to start off by plotting the y-intercept, which is my plus 0. Then I use my rise over run to go up 2 over 1. And I really don't even need to go any further because I have found the point of intersection. My lines intersected here at 1, positive 2. So that is the solution for this system of equations. The point that lies on both lines is found at 1, 2. And we can always plug that back in and check. When x is 1, y should be 2. So I should have 2 equals 2 times 1 plus 0. And y, on the bottom one, 2 should equal negative 1 plus 3. Negative 1 plus 3 does in fact equal 2. 2 times 1 is 2, plus 0 is 2, so I know that I did it correctly. Okay, so a system of equations, once again, is just two or more equations, and the solution is an ordered pair that satisfies all of the equations. The problem is sometimes we have more than one solution. Let's look at this slide here first. A system that has at least one, meaning that it could have one or more, is said to be consistent. So that first one that we just solved, that first example, was consistent. Once we determine if it's consistent, then we have to decide, does it have just one or does it have more than one solution? If it has only one solution, it is independent. If it has more than one, infinitely many solutions, it would be dependent. Now think about your prior knowledge, I guess, of graphing equations. What would be a system that has infinitely many solutions? When I graph them, if I end up with the same line over top of the same line, every point that's true for one is going to be true for the other one. So that would be infinitely many solutions. So this would be dependent. If I have lines that intersect at exactly one point, then that would be independent. It has only one solution. And think about inconsistent, where there is absolutely no solution. How could we never have any solutions? Well, if they never intersect, they never touch each other, then they're not going to have any solutions. What kind of lines do you know that never ever touch and never intersect? Parallel lines. So parallel lines would be inconsistent because they never touch, never intersect. And what do we know about parallel lines? They have, hopefully you're filling in the blanks here, parallel lines have the same slope. So lines with the same slope are going to be inconsistent. They're never ever going to touch, unless, of course, my marker's not working down there for some reason, but unless, of course, they end up being the exact same line. If they have the same slope and the same y-intercept, then they're dependent. If they have the same slope and different y-intercepts, then they are inconsistent. Okay, so let's look at some more examples. 8th grade math, you probably learned how to graph equations. Actually, I know you did. So we're going to take it a step further, and you not only have to graph, but you have to write the equation, you have to graph, and then you have to find the point of intersection. So let's look at this problem. It says, scientists studied the weight of 2 alligators over a period of 12 months. The initial weight and growth rate of each alligator is listed below. After how many months did the alligators weigh the same amount? I would like for you to pause the video and try this on your own. Okay, so it says the initial weight is 4 pounds. We know that that's not a varied rate. That is the set weight for the alligator when it was first weighed, so it's not going to have a variable with it. It's set in stone. But then we know that the 1.5 pounds per month means that they were gaining a pound and a half each month. So since we're talking about graphing equations here, I'm going to rewrite this as 3 halves. 3 halves will make it a lot easier to graph. 3 halves is the same as 1.5. Okay, so per month, let's let x be our number of months. And how would I write that they're growing by 3 over 2 pounds per month? I would just put 3 over 2x plus their initial weight is going to give me y, their total weight. Okay, so this alligator, number 2, weighed 6 pounds to begin with. Once again, this is not a varied rate. He weighed 6, it's not changing. I mean, he's gaining weight, but that 6 pounds doesn't change. From the first time that we weighed him, he weighed 6 pounds. That's the way it goes. And then he gained 1 pound per month. So once again, I want to let x be the number of months. So 1 pound times the number of months plus the 6 pounds that he weighed to begin with gives me alligator 2's total weight. So now we can graph these. Looking at them, I know they don't have the same slope, so they're not parallel. And I also know, since they don't have the same slope, that they are not the same line. So they're not parallel, they're not the same line. So I'm guessing that they are going to intersect at one point. And we can plug it in and see. Let's graph this alligator 1 first. So I'm going to go up 1, 2, 3, 4, plot the y-intercept and use my slope. Up 3 over 2, up 3 over 2. And I'm running out of room on my graph, so I'm not going to be able to go any further, but hopefully that's far enough. Let's go ahead and plot alligator 2's weight. He starts at 6 pounds, but he only gains 1 pound a month. So up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And that was enough, thank goodness. Our point of intersection, we can see, is right here at 410. So now what we have to decide is, what does that mean in terms of this problem? The question asks, after how many months did the alligators weigh the same amount? Well, we know that the y tells us their total weight. So we know that they weighed 10 pounds at the same time. And the x tells us the month. So when x was 4, after 4 months, both alligators weighed 10 pounds. So after how many months did they weigh the same? 4 months. And I was right. There is one solution. So we know that it is consistent and it's independent because there's exactly one solution. Okay, let's try this one. Let's graph it. We've got 2y minus x equals 2. The problem is, with this top one, it is not in slope-intercept form. So the first step is always to put both equations in slope-intercept form if I'm graphing. So if I have 2y minus x equals 2, and I want to put that in slope-intercept form, I know I need to move the x to the other side, so y is all by itself. So I have 2y equals x plus 2. And then to get y by itself, I divide everything by 2. So I have y equals 1/2 x plus 1. That looks oddly familiar. It's the exact same equation as this. So if I was to plot the blue and then plot the red, they're the exact same line. They have the same slope, the same y-intercept. Therefore, we know that one lies on top of the other one. So I don't even need to graph it to tell you that it is consistent. There's going to be a solution. But there's infinitely many solutions because they're the exact same line. So it is consistent and dependent because there's more than one solution. Okay, let's try another one. Y equals 2x plus 2 and y equals 2x minus 1. Now, I could go ahead and plot these, and we will. We'll go ahead and plot them. But before I even plot them, I know that they have same slope and different y-intercepts. We know that parallel lines have the same slope. Parallel lines never intersect. Therefore, there would be no solution for this system of equations. If it has no solution, then we say it is inconsistent. So let's graph it just to double check. Go up 2 for the y-intercept, and then my rise over run is up 2 over 1, up 2 over 1, and there's my line. Okay, this one starts down here at -1, and the slope is still up 2 over 1, up 2 over 1, up 2 over 1. And we can see that they're never ever going to intersect. They are parallel. Therefore, they are inconsistent.